Hello, everyone. Welcome to iCast. I want to start this episode off a little differently than usual. I want to give our technical crew a big shout out because I feel like they haven't been represented enough in these episodes. So a big shout out to Alan Zheng, who has controlled all of our technology throughout the whole series, and Gabriel Lavandera, who has been in the background helping with any support we've needed. He even today bought a little souvenir from the book fair that we went to, the coconut plant.
That's
and
great.
I'm hoping this will stay with us for the longevity of iCast.
Quite a work of art, I have to
love
tell
it.
you.
Yeah, I love it. It gives the podcast vibe, does it not?
Absolutely represents
does,
the Miami culture, the palm trees.
Okay, jumping straight into the episode. We are here today with a little bit of a different episode. We will not be having a one-on-one interaction like we usually do. Rather, me and Nicholas will be explaining to you guys the beauty of mathematics. So, Nicholas, if you want to give a quick intro.
Yeah, so my name is Nicholas Rivadero. I am a AP Calc AB student, Calc 1. And yeah, I love math. Math is a passion of mine, and yeah, I hope I pursue it in the future.
And we have a very special guest who was willing to listen to Nick rant on about mathematics as well as me, Jonah Epstein, if you want to give yourself.
Hello, everybody. My name is Jonah. I don't know about you guys, but I'm personally excited to hear and learn a lot about the beauty of math and its applications into the world. So let's get started.
Let's get started, Nick.
All right.
Okay.
So, okay, first I wanted to start off by talking about how math influences our world, right?
Okay.
So some people usually think, well, a lot of people, right, that pure math doesn't really contribute to our society. They'll think, oh, these guys just sit in a lab all day or sit in a classroom all day just doing math. But in reality, it's all around us, right? So take a look at your phone, right? What do you see? You see your text messages, your time, your screensaver, whatever, right? But in reality, there's so much that goes through it that all of it is math. So here, I'll give you an example, right? Cryptography, okay? Have you guys ever heard of cryptography?
No. What is
Personally, no.
cryptography?
Okay, so cryptography is basically the study of secure communication, okay? So basically what that means is that people who study cryptography study how we can have more secure communication between two people or more,
Okay.
right?
Oh, so it's like encryption.
Exactly. So
Oh, okay.
Yeah, encryption.
It's a lot regarding national security.
Exactly.
Okay, got it.
It's integral to
Yeah.
whatever type of communication that we have. So yeah, as you said, encryption, right? I just wanted to talk about that a little bit. Do you guys know a little bit about encryption?
I just know that it's like how you communicate safely with other people so other people can't see what you're doing.
Right, yeah, exactly. So I'll give you guys an example, right? Let's say you want to send a text message like, I'll be there at 4, okay? So the way you're going to send it, which is the sender and then the receiver, it's going to be the same, right?
Yeah.
But while it's going through, it's being encrypted. So it's going to look something like with hashtags, ampersands, things like that, right? Like
Yeah.
all these types of symbols and numbers, just to make sure that if someone were to intercept the message, it would be encrypted. Okay,
Yeah.
you wouldn't be able to see. So it's a very safe way, right? And the reason why I wanted to talk about this is because cryptography and encryption have a lot to do with prime numbers. Okay, so have you guys ever heard about prime numbers?
I have a basic understanding, but you want to elaborate maybe?
Yeah, and this is one of my favorite topics.
Yeah.
It's really
So
extensive.
prime numbers, just like for a basis, is a number that can be divided by itself in 1. So I'll give you the first set of prime numbers. It's 2, 3, 5, 7, 11, right? So those are and then it goes 13, 17, and it keeps going, right?
Yeah.
So the reason why we take into account prime numbers is mainly because of its spontaneousness, right?
Okay.
So right now we see the pattern of prime numbers, but as it increases to infinity, it becomes more and more dispersed, and we don't really know the pattern of prime numbers and how many there are, but we have made some approximations with several different types of functions and formulas,
Got it.
right?
Okay.
And so the reason why prime numbers deals with encryption is because let's take into account 2 prime numbers, right?
Okay.
10,009 and 10,007, right?
Okay.
We know that those two are prime numbers, and then if we were to multiply it together, it would be some type of random digits. It'd be like 10 million something 63, right?
Now, I have a question. Is multiplying 2 primes, does that give you a prime?
Not usually. No.
Okay, got it.
Okay.
Because when you multiply, it doesn't become a prime. It just it becomes a totally different number, right?
Okay.
It's divisible by what it was just being multiplied by.
And 1.
Exactly.
Got it.
Well,
Okay.
it's divisible by itself, 1, and then those two numbers that you just multiplied
Yeah,
by.
of course. Got
so
it. Okay.
then it wouldn't be a prime number, right?
This might be a pretty basic understanding of prime numbers, but I feel like it has to do something with the unit digit of the number. Am I sort of right in like a weird way?
So yeah, I mean, it has to do with all of the digits, right? It's very easy to take into account what numbers we're multiplying, but it's very hard to get back to the numbers that we were at, right? Because there's so many different things that we can divide by. Right?
I get what you're saying, Jonah, that the last digit in the number usually dictates whether it's a prime or not. So if a long number ends in 7, then it'll be
exactly.
a prime.
That's what I was
exactly.
trying to
So
say.
yeah, usually if it's something like 10,009, for example, right? It's because it's something like 10,000, but then it's a 9, right? And 9 is usually divisible by 3, but if we add it to a number like 10,000, then it doesn't become divisible by 3. Does that make sense?
Yeah.
A little bit?
Yes.
Because 10,000 can't be divided by 3.
Yeah.
Exactly, right? So, yeah, that's basically a brief understanding of it.
Okay.
And so that deals with mainly encryption, right? But like the spontaneousness and how we use it to encrypt, right?
Yeah.
And what stems from that is our mathematical theorems. So things like the Riemann hypothesis. Have you guys ever heard of that?
I have, and it's
Okay.
one of the most intriguing problems
So-
I've
I've heard of it. I
You've
don't
heard
really
of it.
know
Okay.
what it's about.
Get
Though.
ready for a...
I'm definitely excited.
So, do you want to give like what your understanding is, or do you
Yeah.
just want? Okay.
No, I'll start because I have a very basic understanding. I know you know a lot more.
Yeah,
For
a little
me, the way I know the Riemann is as a young student, I was very interested by the 7 millennial problems.
Right.
So
Yeah.
when I started researching more and more into these 7 millennial problems, I had realized that the most important one in our world of math had been the Riemann hypothesis. Previous to that, which we'll talk about later in the episode, the most important problem in math was Fermat's last theorem. But we had shifted into the Riemann hypothesis after it was solved. And I know it has to do with the counting of prime numbers, the pattern that emerges. It also has to do a lot with infinite series.
Yes,
1
exactly.
over n to the s. if
Exactly.
I'm not wrong.
Yes.
And yeah, that's what I know about it. If you could explain a little more
So
about
yeah, let's start with the basis of what the Riemann or what the zeta function is. So the zeta function relates to the Riemann hypothesis because the zeta function was made by Leonhard Euler, right?
Okay.
Just with real numbers. So a basis of what real numbers are is just like countable numbers that don't contain an imaginary number.
Yeah.
You guys know what an imaginary number
Yeah.
is?
You have,
So it's
you have different sets of numbers. You start with your natural numbers, which is your
Yeah.
positive counting. Then you have your integers, backwards and
Yeah.
forwards.
Whole
your
numbers too.
Whole numbers.
Your rational that you can
Rationals, yeah.
you can make a ratio out of 2 integers
Yeah,
out
exactly.
of, and then your irrational, which is not possible.
Yes,
And then the concept that encompasses all those numbers is the set of all real numbers.
Okay, I definitely want to hear you continue, but there's something you said that I just didn't really understand. What are the 7 millennial problems?
Okay, so
a
the
good one.
Clay Institute of Mathematics, if I can remember all of them.
Okay. Just like a basic overview.
They proposed the 7 most important problems of our generation
Oh,
in
okay,
mathematics
okay,
and
okay.
unsolved. And they offered a $1 million prize for all 7. Let me try to get you all of these 7.
As in math, like 7.
The Poincare conjecture, which is the only solved one. Then you have the Yang-Mills and the existence mass gap, which has everything to do with physics. The Navier-Stokes, which is also physics. You have NVNP problem, which is computer science.
Okay.
You have the Hodge conjecture, the Birch and Swinnerton-Dyer conjecture.
Okay.
These are all math. And then the Riemann hypothesis.
Yeah.
Those are all
Nice.
7.
Okay. Yeah.
Okay, you remembered all of them. Nice.
Yeah, so back to the zeta function,
Yeah.
right? So the zeta function was created by Euler. I don't know if you guys know Euler. He was one of the best mathematicians of all, arguably the best that added to pure mathematics. It's a big debate.
Greater than Nicholas Rivadero?
No, obviously, yeah. I mean, I'm not at that level. Hopefully, I will be.
Don't worry, you'll
Right.
get there.
Yeah. So yeah, Euler was great at everything. I mean, he created one of the best irrational numbers, E. Right.
That's Euler's number.
Yeah, Euler's number.
Euler's number, right? So the zeta function was created by Euler, so it was 1 over n to the s.
Yeah.
But what Bernard Riemann did, and that was the other mathematician that created the Riemann hypothesis, named after him, right? Was that he stated that for every non-trivial 0, and then let's stop right there. So non-trivial just means that it contains an imaginary number, right? So it's going to be something like 3 plus 2i. And so 2i would be 2 times the square root of -1.
Yes.
Because we can't really solve square root of -1.
I is the square root of
Exactly.
-1.
So we make it a complex plane.
Yeah.
Yes.
In math, up to what you've learned, you've only worked with the real number, with the real coordinate plane. Then you start, in later math classes, start working with the imaginary plane, which becomes a whole different set of mathematics.
Okay.
And that's where this whole problem lies on, the imaginary plane.
It's like your whole life you focus on like math and like concrete digits, and then
Yeah.
you get into imaginary numbers and like how can you calculate
Like
something
that,
that's not real?
And yeah, mathematicians found a way.
Exactly.
Yeah, it's incredible, honestly.
It's phenomenal.
Yeah.
And that's where complex analysis comes into play, which is a little more complicated. But yeah, so basically what Bernard Riemann said was that for every non-trivial zero that existed for the Riemann zeta function, it would have a real part of 1 over 2, okay? So that means that if you plugged in 1 over 2 and then you plugged in another rational number times I, then it would be a non-trivial zero if it, so if the imaginary number gave you a 0, if it resulted in 0, then it must have a real part of 1 over 2.
Yeah.
That would be its input.
And now, for the viewers who didn't fully understand that, because
Yeah,
I'm sure there's a lot of you, the important part to remember here is that Riemann posed a hypothesis. Remember, it was a hypothesis. He said that this should be true. And up till today's numbers, meaning a lot of computer analysis has been run, there has not been a single number that has disproven his hypothesis. And we've gone into very high digits.
But it's not possible that it couldn't be
Exactly.
proven wrong.
As you go into infinity, can we assure ourselves that there is a number that doesn't disprove this hypothesis?
Exactly.
And that's the problem with a lot of these mathematics nowadays. We can't prove these hypotheses, conjectures, without assuring ourselves there isn't a number close to infinity or to a higher degree of infinity that will not disprove this.
And so that's where like kind of the problem of computational analysis comes into play, is because it gets to such a high point of infinity that we can't really calculate what the number would be, right? So back to what we were talking about at the beginning with the distribution of prime numbers.
Yes.
This is where it gets interesting, right? Something that's absolutely crazy is that when we line up the distribution of prime numbers, so which is called the prime counting function, introduced by Carl Friedrich Gauss, which was phenomenal mathematician.
If you need to know two mathematicians in your life, it's Gauss and Euler. Those are the two.
Cool.
Personally my favorite, but they're just great. They've made so many contributions to the world of math. But anyways, he introduced the prime counting function, which is basically saying that the input of a number gives you an output of how many primes are up to that number. So let's say we plug in 11, right?
Okay.
So it would look something like the function of 11 is equal to, let's see, it's 2, 3, 5, 7. And so, that would result in 4, right? So then that would be our result. And it would look something like a staircase because...
is there an equation for this?
So, there's an approximation. So there's two approximations that we know of so far, which is the regular prime counting function, which is just x over the natural log of x, okay?
Wait, give me a second there. X over the natural log of x. Okay, got it.
So for
log base e.
Exactly. So a log base e of x. Yeah.
Yes. Okay.
And go ahead.
No, go.
Oh, okay. So then we come to something that's pretty complex, so I'm just going to briefly touch over it, which is the logarithmic integral expression, okay? And that's basically just an integral from 2 to whatever number you're trying to find of 1 over the natural log of x with respect to x, okay?
You lost me.
Yeah.
Can you go back a second?
It's incredible that we're explaining it in this detail, but for the viewers that know a little less about
It's a little complex.
Let's kind of break it down.
Okay, so basically what's happening is that, so to explain an integral very briefly, it's just the area of under the curve, right? And so we have a lot of different processes to calculate what the area of under the curve is. But in this case, it would just give you, so that function would give you a very, very close approximation of any number that you plug in as it goes to infinity. So the bigger that it gets, the more accurate it gets compared to the original one that we had, which was x over the
it's
natural
possible to quantify infinity in the term of an integral? Because under a curve, that's infinite space in a coordinate plane. So how can you calculate the area of an infinite space when it's constantly evolving?
So I'll explain that part, which did confuse me a little when I started calculus. It's actually not. So I think the confusion you have is, let's imagine a quadratic. It's not the quadratic. Let's say we're talking about the height. It's not the quadratic all the way down. It's just the quadratic to 0.
Oh, okay. So the x-axis.
So, for example, for a negative function, it'll measure negative space under the curve.
Okay. So it goes from the tip of the parabola to the x-axis.
Exactly.
Okay.
Exactly the point, yeah.
Because if we didn't include the x-axis, then it would just be infinity.
You're right. Yeah. That's what I was a little confused about.
Exactly. Where was I?
No, okay. Back to the Riemann.
Yes.
Okay,
It's
yeah.
Riemann's and
So the
integrals.
Riemann. So yeah, that's where it comes into prime numbers. So basically, the distribution of our non-trivial zeros, like as I've stated, the imaginary zeros. Is so incredibly close to the distribution of the prime numbers of those two functions that if we were to prove the Riemann hypothesis to be true, then the distributions of prime numbers would be very, very accurate to what we have today. So right now we assume that the Riemann hypothesis is true, but we're not really sure. Well, obviously we're not sure, right?
Yeah.
And if it were to be disproven, then it would have a lot of errors in cryptography.
Yeah.
Since we assume that prime numbers would go, well, we don't know if prime numbers go on forever, but we assume.
Yeah.
And they go on in a very sporadic way, right? So, yeah.
And that's one of the things that we actually know, that prime numbers, as they reach infinity, become less frequent.
Yes.
So the proportionality to the amount of numbers you have and the prime numbers within those numbers becomes a lot less than from the amount of prime numbers 1 to 20.
Okay. Tying this back to cryptography. So you were saying how the number of prime numbers as we go closer to infinity decreases. How does that relate to cryptography? Because I believe you mentioned something about how because it's spontaneous and there's less of them, that it's better for cryptography.
Well, the thing is that it doesn't really become less, it just becomes less frequent.
Less frequent, yeah.
So so as we go into infinity, the prime numbers that we start seeing become less and less frequent. Like we might see one every 1,000th as we go into infinity, something like that.
Yeah, exactly.
And there's not really a set pattern other than those prime counting functions that are only an approximation. They'll never give you a for sure answer. There's a lot of error.
When we connected it back to the Riemann, which was the beautiful part, we actually realized that there is some sort of structure if we are able to prove the Riemann. And I think the coolest part about all this is to show that computational analysis, as to date, cannot beat the human hand. Meaning, if we put in the Riemann zeta function into a computer, it cannot tell you a certain amount of numbers that will disprove or prove it. Do you understand that?
Yeah.
Because no matter how high we go, there will always be numbers higher than that could potentially disprove this certain hypothesis. That's why, as to date, we still rely on the human hand to disprove this sorts of things. The theorems that mathematicians posit for these sorts of problems are beautiful, complex, but still beautiful. And that's where I find the beauty in mathematics.
Exactly. And honestly, the reason why I'm so focused on the Riemann hypothesis is because it's so interesting. Like, it almost gets me emotional because it's so crazy to see that for every non-trivial zero, it lines up to a straight line.
Okay.
And it's just like it's so complex to understand, but as you get to it, it just makes it makes sense, and it's just it's incredible. It's beautiful.
Yeah.
That's why math is beautiful.
And another thing I wanted to talk about was another major problem in mathematics. Right. So we're going to shift a little bit from the prime counting functions and Riemann hypothesis to one of the biggest unsolved problems in math as till the 1980s, the Fermat's last theorem, if you want to elaborate a little bit on.
Yeah, so the Fermat's last theorem, I don't know if, Jonah, you've ever seen...
Vermont or like the state Vermont?
No, Fermat.
Like fermentation, like
exactly.
Vermont and fermentation.
Fermat.
So back then, Fermat was a famous mathematician, and he was one of the highly regarded mathematicians. However, he did have one problem, which is a problem I think a lot of us have in math class. He would show a lot of theorems, yet show zero proof for all of these theorems. So no one could actually take him seriously as a mathematician until they started looking at these theorems he proved and realized that the majority, if not all, were actually true, until they got to his last theorem, which was kind of mythified in mathematics. And it was not proven until the 1980s. That means he was ahead of his time by 100 years.
And so that's why we call it Fermat's last theorem. It was the last theorem that we ever saw of Fermat, right?
Okay.
And basically, I don't know if you ever seen the Pythagorean theorem.
I have.
So what is it?
It's
A squared?
A squared plus B squared is equal to C squared.
squared,
You're right. I blanked for a second. I know it though.
Yeah, and to keep it simple, it's basically that. It's A to the n plus B to the n equals C to the n.
Okay.
And Fermat posited that no number greater than 2 would satisfy that theorem. And it took until the 1980s, 1990s, where English mathematician Andrew Wiles was able to prove this when he realized there was actually a discrete connection between elliptical curves and Fermat's last theorem. There was a conjecture in elliptical curves, I won't go too much into it, that said every elliptical curve has an equal modular form. And if mathematicians were able to prove this elliptical conjecture, they were actually able to prove Fermat's last theorem. And it took him a while, which is one of the most beautiful stories in mathematics. I would very much encourage you to watch his interview after he solved it, one of the most emotional interviews in my... And he actually was able to prove it showed his findings to a society of mathematicians. Only 6 people in the world were panel of judges being able to review this proof he put forth, and they told him that there was a problem with the proof. He went back. For a year, he spent trying to revise this problem. He was about to give up until his colleague said, let me get back to Cambridge, where he was. I'll be back in a month, and then you can quit. And within that month, he was able to solve all of it. He was able to tweak the Coley-Vaughan-Flock method, which is a very famous method in solving elliptical curves. And in these tweaks, he finally solved it, and that interview shows me the extent the human mind can reach.
I agree with you. I don't comprehend completely the math you're talking about, but what I do comprehend is the persistence and hard work it takes to solve.
It's incredible. By the human hand. It was, if I'm not wrong, 129 pages that proof.
Wow.
Pure mathematics.
Me personally, I like to keep my English and my math separate, but you have to
it's
prove
a book.
it.
It's a full book.
Yeah.
It's incredible.
Straight math. Imagine only 6 people in the world were able.
I think that's really interesting that interests you guys. I mean, it interests me too. It's just on a different level.
And I'm glad we were able to have this conversation about mathematics.
Thank you
today.
so much, Mateo.
I'm glad we were able to visit this conversation. And we always like to end with our famous lightning round. I did ask these contestants, not contestants, I did ask these guests before the podcast whether they knew what the lightning round was, and they did not, so I'll explain it really quick.
No clue.
I am going to ask you, starting with Nick and then going to Jonah, a question, and I need 1 word straight response within the second, okay?
1 word straight response, okay.
You ready?
Yeah.
This is a lot of pressure because a lot of our guests get tripped up by this. Okay, our famous question, is a hot dog a sandwich?
No.
Okay.
Ooh. Close call.
What do you think?
Yes, a hot dog is a sandwich because there are 2 pieces of bread with meat in between. Just because the content of the meat is shaped like a dog, well, no, it's a hot dog.
I thought it was 1 word.
Okay, you're right.
I actually agree with Nick, as I've made clear in the show. I don't think it's a sandwich.
You don't think it's a sandwich?
Nope.
Define a sandwich to me.
Okay, let's move on because
Okay.
Okay, now second. Favorite TV show to go back to after school?
Wow, that is difficult. I'm not going to lie. Skip and go to Jonah.
Okay, Jonah.
I'd like to skip and go back to Nicholas.
Okay. I don't know. It's a tricky one. SpongeBob. I love it.
Bubble Guppies.
Okay, but real show.
No, I'm serious. Like, I've actually watched Bubble Guppies multiple. No, actually, no. Wait, what was it? SpongeBob. Honestly, it's SpongeBob. Like, you can't go wrong with SpongeBob.
You really can. It's incredible.
I haven't watched those shows for at least 10 years of my life. Okay.
No, honestly, I don't really watch those.
No, this one's more for Nick, unless Jonah wants to give an answer.
Okay.
Who is your favorite physicist, mathematician / scientist of all time? I'll give my answer to this.
That is an incredibly hard question.
I'll give my answer.
One mathematician. Wow. Carl Friedrich Gauss.
Okay. Do you have any answer that you want to give?
Of course
it can be
I do.
a scientist. It can be...
I'll tell you who my favorite physicist is.
Okay.
The man, the myth, the legend himself, Nicholas Rivadero.
Thank you, Jonah. Thank you.
No problem.
Mine would have to be Marie Curie.
Marie
She
Curie.
is one of my biggest
Okay.
inspirations in this journey of mathematics I have decided to take. And Richard Feynman, a great inspiration
That's
to all.
incredible.
That
Okay,
hard
yeah.
work
It
alone.
really is.
The IQ doesn't just dictate your persistence in your field.
You're right.
Pure
Yeah.
hard work and consistency will also get you to successful places.
I agree.
Okay, now final question. We always like to ask our viewers this, our guests this. Give one last piece of advice to our guests, to our audience.
Okay. When everything seems to go wrong, keep going. Because at the end of the tunnel, there's always a light.
Okay.
Now, Jonah.
My advice for the viewers out there is even if you don't understand something or if you don't comprehend the complexity of math, there's always more you can learn.
Yeah.
Even the people who are the best at math, there's more you can learn. Be persistent, stay dedicated, and do what you love.
And I'll add one to this. I don't usually add one, but I'll add one to this one. When you go to school and you wake up in the morning, I know for at least 90% of students here in Miami, here in the country, the one class you dread going to is math. It's a class that you wake up not wanting to go to. Yet, my advice would be always keep an open mind to stuff you don't like.
I agree.
I was able
Yeah.
to keep an open mind to mathematics. I never disliked it, to be fair.
Yeah.
But in my keeping an open mind, I have been able to discover another world that I did not think was possible. That
Yeah.
I did not think was possible just by the human hand and brain. And I have discovered, with the help of some of our great teachers at iPrep, Mr. Major, Miss Hinkalari, who is now at Ransom, that I have found my passion in life. And I encourage the viewers to find theirs by just opening their mind to stuff that they might not like. Whether it's mathematics, whether it's biology, 100%. Whether it's chemistry. Keep your mind open to all these subjects.
And real quick, I just want to say, you're not born with intelligence, okay?
Yeah.
I agree.
You both
Intelligence is persistence and hard work.
Yeah.
Absolutely.
And a little bit of genes, just coming from biology.
Thank you so much, Mateo.
Yeah.
This has been awesome.
Thank you guys for coming here and having a podcast with us. This has been one of my favorite podcasts because it's a topic I'm heavily interested in.
I agree.
And thank you so much.
Thank you.
Let's give our iCast viewers a final goodbye. Bye, guys.
Goodbye.
Goodbye.
iCast viewers. Hasta la vista.